Okay, so hello, welcome to week 4 of the CAD and 3D printing class. Uh, we're just going to kind of hop straight into it, and we're going to be talking mainly about 3D printing and your final projects. So here, I'm just going to introduce you to the final project. You've definitely seen this slide before, but I'm going to go over it again now that you know a little bit more. Again, final project basically is free reign to make whatever you want. Obviously, it just can't be something that we've already made. I feel like that's self-explanatory. But the one thing that you might understand better now is that it must contain at least 5 design features, right? So a design feature could be, an extrusion or a valve or something like that, or a loft or a sweep. You just need at least 5 of those in your feature tree. They could be like more than one of the same type of design feature. Like you could have 2 extrusions and that counts. But you'll kind of figure out pretty quickly that 5 design features is not that bad. Like for some of the things we've done in class, we've probably done over 5 already, especially for that hair dryer thing. I think that's pretty close to 5, if not more than 5. So these requirements are very lax, but we encourage you to try your best and push yourself to make something really cool. You've seen, I think it's on the next slide. Yeah, you've seen this slide as well, where you can see some past finals. These all definitely have more than 5 design features on them, but they kind of push themselves to kind of make something cool. And I think it's really awesome when that happens, but I also know that this class isn't always the priority for some. So if you need to just crank something out real quick and send it, then that's fine too. But yeah, just keep that in mind. The last thing that is a little bit more subjective is that it must be designed with manufacturability in mind. So if you're curious about what that means, I'm going to be talking a lot about that today, because the medium at which your finals are going to be made is 3D printing. So if you want your final to be designed or to be printed, it would be great if you designed it to be printed. So, I have a better time printing it and you don't get a pile of scrap for your final, because that would be sad. So yeah, that's basically what we're going to talk about today. All right, so designing with manufacturability in mind. So there's 2 main types of manufacturing. The first one being subtractive manufacturing. When you think about like movies and stuff like that, a lot of the times when they have like the montage of the person making something, it's usually some kind of subtractive process, right? You'll see people like grinding or cutting things away, and sparks are flying everywhere and stuff like that. That's usually some kind of subtractive process, because you're starting out with some raw stock or material and you're cutting away at it until you have your final product, right? So you can kind of see here on the left, we have that square, you have some kind of tool that cuts away, and then you have a final product. So, these are some examples of different subtractive processes. Drills and mills, lathes, all of that is subtractive because you're taking stuff away. Grinding and stuff like that is also a subtractive process. That's something that I kind of forget about sometimes. But yeah, a lot of these processes are great. They're really nice and precise when you have a nice rigid machine, but those machines are typically really expensive. So like a milling machine can be like thousands of dollars to north of millions of dollars. And I don't know about you, I don't really have $1 million to burn. I'm buying like a nice Haas CNC machine. So I usually don't do these subtractive processes. So yeah, they're typically available for, larger companies. But if you need a really strong one-off part, sometimes you can pay someone to do it. But the other thing that we're mainly going to focus on today is additive manufacturing. So a lot of you will think of this as 3D printing. Basically, you start with some kind of material and you extrude it out of some tool, oftentimes a nozzle, and then you'll, add it to material until you get a final product, right? So again, very kind of self-explanatory. You're adding stuff, but if you didn't know, additive manufacturing isn't just 3D printing. The injection molding additive process, or is also an additive manufacturing process, but that's mostly reserved for high volume production because a mold for an injection molding machine is usually pretty expensive. So again, injection molding is kind of out of scope for students like us. So we usually fall onto 3D printing nowadays because it's gotten more and more accessible. So again, I'm a very big 3D printing nerd, so I'm going to talk your ear off today, so I apologize in advance. But I hope some of the wisdom gets instilled upon you. There's a bunch of different applications to 3D printing other than printing fun desk toys and stuff like that. It's making its way into, industry, being sometimes commercially viable. It's great for rapid prototyping and development for, something that might become injection molded or, milled later. So it's a good way to make things quickly, iterate quickly, which is why we typically associate it with rapid prototyping. It's great for aerospace applications because you can precisely control what material is where without having expensive tooling costs. So you can make a part really light while making it still relatively affordable. You can it's starting to make its way in the automotive scene, though it's mostly on like bespoke, like really expensive cars. There's a company called C. Zinger, I think, and they're based out of California. And most of the chassis and all the suspension is all 3D printed. So you can see on the right photo, you can see it's a very organic looking shape. That's all 3D printed. And in many cases, it's the only way you can manufacture that part. So yeah, 3D printing is pretty cool. There's 3D printing houses now. Some people may have heard of that, but there's a bunch of different applications. I think they print like pancakes and stuff on like the ISS with a 3D printer. I don't know. I thought that was interesting. Anyways, there's many types of 3D printing aside from pancake 3D printers. A lot of the more industrial focused ones will use something called SLS or SLM printing. It's kind of when they take a powder of some material. SLS is selective laser sintering, which is usually some kind of plastic or polymer. But they basically have a very fine powder. They lay it out in a layer. They use a laser to melt it. And then they put another layer of powder above it. They shoot a laser at it again precisely. And it slowly builds up layers and layers until they have a very nice 3D printed part. SLM is the same process, but instead of for a polymer, they have it for metal. So you can 3D print like stainless steel and stuff like that too, which is pretty cool. I don't have that on the slides, but it's basically the same thing. But again, it's a little bit harder for us to do that as students. So we typically rely on something called SLA or FDM 3D printing. FDM's on the next slide, but SLA is a little bit less common because it uses a kind of resin instead of a plastic. It's a UV curable resin, kind of like an epoxy, and you basically have a vat of it and a build plate, and then you have a UV light underneath that's almost like a TV, and it'll shine a precise area of UV light. It'll partially harden the material, and then it'll go up and it'll do it over and over again. And then, you have to clean it, and then you have to cure it and stuff like that. So SLA is pretty cool. It makes very highly detailed parts very well. But typically the setup is a little bit more annoying because you have to deal with liquids and a bunch of other stuff. So it's not as common, but it's also pretty cool. People like to use it for printing miniatures and stuff. If you do like Dungeons and Dragons, people do that. People use SLA for that a lot. So, yeah. All right. Okay, so the main one we're talking about today and kind of the rest of this class is FDM 3D printing, because that's what your finals are going to be made out of. I would say it's probably the most common type of 3D printing that most of you are familiar with. There's two different names for it. There's FDM and FFF. The only reason why they're two names is I think Stratasys has a trademark for FDM, so everyone else has to use FFF, but they're kind of interchangeable. They basically do the same thing. So I might refer to them as FDM or FFF interchangeably, but they mean the same thing. So yeah. So if you didn't know FDM 3D printing, I like to kind of simplify it as a very fancy hot glue gun that extrudes plastic instead of glue, connected to some kind of robot, right? So there's some form of heater that will melt the material, some kind of extruder that pushes that material through, typically controlled by some kind of motor, and then that assembly is connected to some kind of kinematic system that moves it around. And with precise control of a computer, you can, deposit material pretty accurately and in many cases now pretty quickly. So, I'm sure a lot of people maybe have 3D printers of their own at this point. But if you didn't know, that's just kind of how it works. Yeah, it's pretty cool. So now that you hopefully know what, in general, what 3D printing is like, I'm going to kind of go into the nitpicky part of all the different settings. I'm not going to cover every single setting today, because if we did, I'd be here for more than 10 hours, and a lot of them aren't super relevant in most cases. So I'm going to go over the major ones. The first one is the layer height. So if you think of your 2D printer, I don't know if you've messed with the settings before, but you can change the DPI on some printers sometimes to get higher or lower resolution. The layer height on a 3D printer is similar, but in the Z direction or in the vertical axis, right? You can change how precise your resolution is on the Z axis. And there's different benefits and advantages or disadvantages depending on what setting you choose. So yeah, a lot of these settings I'm going to talk about today are very dependent on what application you're using them for. So I'm just kind of giving you an overview of what they all mean so you can pick the right setting for your application. So for layer height, it's basically how coarse or how fine the layers are. You can see on the left side, there's a 0.8 millimeter layer height. And if you look closely, you can even see the layer lines on the printer, right? So if you're looking for something highly detailed in the Z direction, you might not want a very coarse layer height. But if you want something printed really fast, then you might want something at a coarser layer height, right? A coarser layer height generally means you have to print less layers, which means the printer has to make less movements and it will typically be faster. So if you need a part really quickly, you can reduce that layer height. Obviously, if you want something to look a lot nicer, you might want to decrease the layer height. So you can see as you progress to the right side, the layer height is down to 0.1 millimeters. It's very fine to the point where it gets a lot harder to see the layer lines. So, if you want something to look nice, sometimes you lower that layer height to kind of reduce the amount of seams that are visible. One thing to note is that 3D prints typically fail along the Z-axis, right? And it's because the bond between each layer isn't as strong as the bond between the material itself. So that's usually a weak point. So if you want a mechanically strong part, sometimes increasing the layer height will actually make the part stronger because there's just less points of failure for the part to shear along the Z-axis. So if you want a really strong mechanical component, some people recommend you increase your layer height to be something a little bit coarser. So that's just some interesting information for you. Other than that, there's perimeters underneath this. It's basically how thick the outside wall is on a 3D print. If you didn't know, most prints are actually hollow because you don't need a lot of that material on the inside. A lot of the strength comes from the outer shell of the part. So it's typically a lot better to increase the outer shell thickness than the density of the inside. So I'm going to be passing around some samples today. Some of them are, I think all of them are marked with the number of perimeters and infill. We're going to go over infill in a little bit, but this might give you a good idea of what's kind of going on inside your prints. But yeah, basically increasing the number of perimeters will increase the wall thickness. And it'll make your part strong. Obviously, if you have more perimeters, your part will probably be stronger, but it'll take more time, right? You have more material that you're depositing, so you're going to need, more time to deposit that material. So again, it just depends on your use case. If you need something to be stronger, you might want to increase these perimeters. But if you want to save some time or whatever, you can decrease that. Nice. But typically, I would say the number of perimeters set by like the standard is usually around 3. Sometimes they do 2. For me, because I make more mechanically or more components that are subject to load, I usually increase it to 4. But sometimes I'll go 6 or even 8 depending on what I need it for. So yeah. On the top here is density or infill density, which is kind of what I was poking at earlier. Again, parts are not always completely solid in nature, so you can control how dense it is on the inside. So I think I'm passing around 2 samples, one at like 25% infill and one at like 15 or something. So you can see the different mesh densities. Increasing that infill percentage will give you a little bit more strength, obviously more material and time. But like I said earlier, I recommend you increase your perimeters before you increase your infill because it's typically faster and it'll still be stronger and lighter. So I recommend that before anything. All right. So underneath that is support material. 3D printers are not a perfect process and they can't make absolutely anything. You'll probably encounter times where you'll have some kind of overhanging area and a 3D printer can't really print in midair, right? When the material comes out of the nozzle, it's, molten plastic. So it'll droop and then it'll flop over. So if you ever encounter a situation where you have some kind of overhanging area, it might be a good idea to add some kind of support material. So supports are basically a sacrificial, amount of material that you print underneath it to support the thing that you're printing. It's kind of implied in the name, but it can be useful in a pinch. But the good thing is, if you're designing a part, you can do your best to design it to not need supports, because supports obviously takes extra time because you need to print the support along with your part, you know, it costs more because you're adding material, but then you also add a step of post-processing, right? You're gonna have to spend time to remove the supports, and sometimes it can get kind of annoying. Obviously, if your geometry really needs that, you know, area of material there, then you can add that support. But typically, because you're designing the part, you have the power to design the need for the support out. So I'm gonna pass around this support that I have. I was printing like a helmet for someone, and you know, a helmet's basically a big dome. So the top of it is a really large overhang. So it resulted in a giant support. Obviously, this geometry for a helmet is kind of necessary. So I needed the supports, but if you were designing something else, then you can remove the need for that. But yeah. Here's another example of supports. You can see here that, you know, the H may not have needed supports because there's two beams and like an overhang in the middle. Some printers can bridge across that gap, but depending on how long it is, it might be a little bit more difficult. I'll talk about bridging in a second. That T, you know, there's nothing supporting the ends of those T's, so printing a support in this direction is kind of necessary. Does anyone Would anyone have any recommendations for the person printing this to remove the need for supports? Yeah, that's right. So, you know, oftentimes if you design something to be printed in a certain way, you can design the need for supports out, right? Obviously, this person printed them straight up, which I don't know why they did, but, you know, if they printed it flat, like you said, there would be no overhanging parts, and then you'd be chilling. But, you know, in the off chance that you really needed it to be printed in that direction because you wanted it to be strong in a certain direction, supports might be necessary. But again, because you're designing things, you can think about print orientation to see if you can minimize supports. Okay, so now that you know some of these settings, we're basically going to download a slicer, which is basically what program you use to convert your 3D models into G-code, which is basically a set of instructions for the printer to follow. So today we're going to be downloading a program called Prusa Slicer. It's an open source program, but there's a bunch of slicers out there. A lot of them are based on each other, or they'll take snippets from each other because they're all open source, and they'll like take good parts of one like program and they'll add it to them. So there's a bunch of programs, or these two other programs, Orca Slicer and Bamboo Studio, are, you know, pretty heavily based on Prusa Slicer, but they all essentially do the same thing. So for simplicity's sake, we're going to just use Prusa Slicer today, but just know that a lot of the things you're learning today will translate to the other slicers, especially because a lot of them use the same code, or the same base code at least. So to download it, you can go under the resources tab. There's that download link here. It'll take you to Prusa's website, and then you can download it real quick. It should be a lot faster than Fusion because it's a lot lighter of a program. So yeah, I already did it, so I'm going to give everyone a couple minutes to get situated. I played like some weird version installed from it, but it's like match what's associated. It's kind of Okay, he needs more time with this. I'm hoping it's pretty quick.
You want us to read out what you do?
Oh, you don't need to log in. Yeah. Okay, so now that all of you have it installed, you should be open to some kind of welcome wizard. It'll take me a second to reopen it, so bear with me. Okay, so you should be greeted to some like welcome wizard that looks something like this. If you go to the next one, it'll ask you to log in. If you want to create an account, you can, but for today, it doesn't really matter. Your Prusa account is just kind of there because it connects with their like repository and stuff like that. Or if you have like a Prusa machine, it'll connect to like all your other machines and stuff. But I'm gonna skip that for today. But it'll ask you what kind of printers you're using. I think it defaults to just all of them, but that's fine. We're going to be mainly looking at Prusa FFF today, but you can see other FFF exists as well. If it wants to load, that'd be cool. Okay, so it should push you to here where you can see there's a bunch of different machines that you can select from. So over here you can see all of the different Prusa machines that they've made over the years. But for consistency's sake, I want everyone to select the same one because we're going to be slicing apart, and assuming you have the same machine and settings, the time for the printer to print the object should be the same. And that's how I'm going to grade. So please select the same one as me. For today, I'm selecting the Core 1L with the high flow 0.4 millimeter nozzle. It's pretty, it's literally the top left one, so please don't select another one. But yeah, once you have that, you can press finish. I'm just going to click through this a little bit more just so you can see what's going on. These are the SLA machines that Prusa has. So if you have an SLA machine, you can select that here. But then you can see there's a bunch of other vendors that, have 3D printers that have presets that you can select. Like, let's see. Say I have a rat rig machine. There's more printers available, but I'm not going to do that today. I'm just going to press finish, and then you should be in this kind of workspace here. So over here on the right, you can see on the top right, there's the different layer heights. So if you click that, you can see there's a bunch of different profiles that you can choose from. Many of them have the same layer height, but they might have some slightly different settings. So some of them might be faster or slower. And then you can kind of see, like, after the layer height, it'll kind of tell you what that profile is geared towards. I'm just going to leave it at the standard 0.2 millimeter speed for now, but we're going to change it in a little bit. Underneath, it's going to ask you to select the filament type. So there's different kinds of materials out there, and depending on what you choose, the print might be faster or slower. So for this, just stick with generic PETG, because if you pick another one, the speed might be different. So please keep this the same as well. Obviously, the printer is what we selected before, which is the Core 1L with the high flow 0.4 millimeter nozzle. If you had more than one printer, if you click this drop down, you'd get like a list, but I only have this for now, so it should just look like that. And then you have some more settings here. So you can enable supports on this drop down. You can change the infill density, or you can add a brim, but we're not really going to talk about that today. But you can kind of see we're missing some settings that I was talking about earlier. So this is just kind of where some of the basic ones are, but if you want more, then there's this print settings drop down on the top left. And if you click on that, it'll give you more options, right? So, there's that layer height there, the number of perimeters here, which is going to be important in a little bit, and then a bunch of other stuff. So when you start tuning your printer and doing different things, you might start messing with these settings, but we're only going to be messing with kind of the big ones today, which is like perimeters and infill and whatnot. You can also change the infill on the infill tab over here. So you can change this. The infill pattern is standard at grid, but you can change it to be different shapes and stuff like that. Again, leave it to grid because it's going to change the outcome of the time. So as long as you don't change too many things, your time should be right. We're going to modify the infill density in a little bit. But yeah, you can also enable supports here. And then there's like the brim and skirt stuff, but we're just going to leave that as is. So to go back to the build plate or the platter, it's just platter on the top left, and then we're back here. You can see this whole workspace here is just a virtual model of what your printer bed is going to look like. So you can add models, and then you can see, how big they are or if they're going to fit. Today, we're going to be slicing a 3D Benchy, which I have a crap ton up here if you want to take some. But it's a pretty standard 3D model. So if you click on this link here, it should take you to the printables page. Printables is like Prusa's repository. So if you like log in, then your account would be connected to this or something like that. But yeah. So for this, we want to just download the whole model. They'll give you a bunch of different file types, but we want the STL in this case. So there's the STL right here. You can download it. And then you can insert it into Prusa Slicer. So you can do file import and import, or just Control or Command I.
Where's it filed with?
What's up?
Where's it?
It's in the resources. There's a link here under the 3D Benchy download. But yeah, you just select the file. It should be an STL file, and then you open it up, and then it'll insert the Benchy into your build plate. Raise your hand if you need more time on this. Oh, you need time. Okay. What's up? Where did I get this? Okay, so now that we have our model here, you can see, it looks nice. But we need to apply the print settings that we want. So the list of print settings I have for like this assignment is kind of atypical, but I just have it here just to make you go through most of the major settings to practice. So typically, like I would print this at like a 0.2 millimeter layer height, but we're going to be doing something different just so you get some practice. So here on this slide, I think it's slide 19, it'll kind of give you a breakdown of what settings I want you to apply to it. So you're going to want to change the number of perimeters, change the resolution or layer height, the infill, and then turn on supports. Again, for most 3D Benchy parts or prints, you never turn on supports because the whole point of the Benchy is if you can print it really well without supports or anything, then you should be able to print most other things pretty well. So, the reason why bench is in the name is because it's a benchmark print. So, yeah. So, I'm going to make these changes. I'm purposely making these changes in this order so you can see what happens. So I'm going to change the number of perimeters to 3, I think. Yeah, 3. Then it says that you want to change the layer height to 0.15 millimeter speed. So if I change it to this, it'll give me a warning that I've made changes to the current profile. If I discard them, then it will change the number of perimeters to the default on the profile that you just changed it to. So in this case, the default is 2, so I'm going to have to change it back. So changing it to 3. I want to change the infill. So I'm going to go to infill, change that density to 20%. And then I want to turn supports on. So for support material, I'm going to turn on auto-generated supports, or you can go to the platter and then select everywhere. So this looks good. Again, make sure your filament is generic PETG. I'm going to hit slice now, and then your computer will calculate all the paths that your printer needs to take to recreate the model. Okay, so you should get something that looks like this. Your time should be in the realm of, 1 hour, 16 minutes for normal mode. I think sometimes Macs have it as 1 minute, 1 hour, 15 minutes or something. But if you're within 1 minute, then you should be fine. If you zoom in here, you can kind of get a good idea of what's going on. If you zoom in really closely, you can kind of see the different layers, right? So if we go to the original model, you see there's a nice smooth transition from the bottom to the top. But because we're printing in layers, there's kind of this little stair-step effect, right? So that just kind of happens with the nature of 3D printing because you're basically taking a part, cutting it into a bunch of horizontal sections, and then making some 2D path, and then going up a little bit and doing it over and over again. A lot of people like to call it, or some people like to call it 2.5D printing because it'll kind of do a 2D profile and then it'll go up over and over again. A good way to visualize this is with this vertical slider. So if you go down, you can kind of see each layer going up from the bottom. You can see the inside is hollow. So this is that 20% infill right there. If you zoom in really closely, you can see the number of perimeters. So the orange one is the outside layer, or outside line, and then there's 2 yellow inner lines. The green is the support material. So this is what you would break away. if you were to print with supports. But yeah, you can kind of go up and visualize it. If you mess with the horizontal slider, you can go layer by layer and seeing the exact path that the printer is programmed to move on. So you can see that arrow represents the nozzle, and if you go across, you can see the path it takes. It draws these lines, just the supports. This orange stuff and yellow stuff is the bottom layer, and then it'll fill it in with that purple. But it'll do that over and over again, in this case, 500 times to make your part. So, yeah. Again, if you were to change any of these settings, the number of layers or the time is likely to change. So, let's say I wanted to do like 0.2 millimeter instead of 0.15. I want to save the infill and the perimeters, so I'm going to transfer them. Every time you make a change, you're going to have to reslice it, right? Because it has to recalculate the toolpath. So it'll do it again. It might be a little bit hard to tell, but the layers are a little bit coarser now. The stair stepping is a little bit more prominent, but you can see the number of layers is significantly less, right? There's only 217 now. So that will result in typically faster times. So you can see here, it's only taking an hour now, just from that one change, right? We still have the same amount of perimeters, the same amount of infill, but if we change that layer height, that time changes. So the time changes obviously will change depending on what setting you apply. But yeah, that's just kind of how it goes. Does anyone have any questions about this? Oh, is it like this? Is it like that?
Yeah.
Yeah, so if you accidentally drag the bottom slider, it'll only show the top half.
Oh.
So you want to like find that bottom slider and you can drag it down. Yeah. Some other cool information is displayed here. You can see like what percentage of time or material is used by what part of the print. So you can see like perimeters take about, 5.22 grams of filament. You can see the support material is like 3.89. This is all kind of useful information. It's kind of interesting that you can see how, this print is only like, 10-ish grams, maybe a little bit more, but the support material adds another like 3.9, almost 4 grams, right? So depending on the material, your print, sometimes your support material will outweigh the part that you're making, right? So it's something to keep in mind if you're going to be printing like hundreds of the same part. If you can minimize the needs for supports, you can make your parts cheaper. So that's kind of nice. Also, like no post-processing, so same thing. Any other questions? I'm guessing some of you have used something like this before already, so yeah. The supports? Like the green? So you need to enable them. So if you, set supports to everywhere, it'll auto-generate supports here. The other thing you can do is you can like paint supports on, but I'm not really going to go over that because it can get a little bit more confusing. But if you select everywhere, it should look like this, and the time should be the same as mine. Obviously, right now the time is wrong because I have the layer height incorrect, but when it was correct, then you should get the same time, which I think is like 1 hour, 15 or 16 minutes, something like that. But yeah. But that's basically it for this assignment. Again, just make sure to take a nice screenshot. It would be nice if I can see the boat. And then also the important thing is the time. So if your time is wrong, I can typically kind of guess why it isn't correct. But again, if you're following along, it should be the same. If you missed it, again, I recorded everything, so you can go back and take a look and see what you may have missed. But yeah, that's kind of it for this assignment. You good? Okay. So now that we have that finished, I'm going to talk a little bit more about the limitations to 3D printing. So we talked a little bit about supports, but now I'm going to go over some different things or some more limitations and other techniques that you can use to kind of mitigate these limitations. So the biggest thing that a lot of people will talk about is overhangs. So basically, your printer is capable of printing something that protrudes outwards from the body below it, but it can only do that to a certain extent. If you continue going farther and farther away, it'll make it pretty hard for the printer to recreate it. So I'm gonna reslice this benchy to kind of show you a good example. So the hull here on this print is an overhang, right? This protrudes outwards from the base. And if you look really closely, you again have that stair-stepping effect, right? So you can see that it needs to place the layer on top of it. And if you have a more aggressive overhang, when it places that layer, it'll protrude beyond the bottom layer with like zero overlap. And that's when things start to droop. So this overhang is like somewhat aggressive. It's not super bad, but you can see here, maybe it might be visible on the second layer. Can I like hide? Yeah, okay. So you can see I like hid the internal perimeters, and you can see these two external perimeters. There's a very small gap in between this, right? In this point, like the material is almost overhanging like by 100%. Like there's nothing supporting it underneath. And when you have that, you start to get drooping and stuff like that, and then you'll need to have supports, right? So if you reduce the overhangs, so let's say you go up at like a higher layer height, the drooping or the overlap is a lot closer. So come on. All right, yeah. So you can see here the layer beneath this one on top has a lot more overlap, right? So that gives it more support and it will be a lot less likely to droop. So that's what people talk about when they talking about overhangs. Generally, the rule of thumb is that you kind of make everything at a 45-degree overhang at a maximum on the z-axis. Obviously, if your geometry needs to be more than that, then it's going to have to do that. But in general, 45 degrees is kind of the gold standard. It's nice because it's in the middle between 90 and 0. So adding a chamfer is a 45-degree overhang. So it's very achievable. Once you start going above that, you might be getting into a little bit more questionable territory. Even though most modern printers are a lot more capable than before, they can do maybe like 60 degrees. That's starting to push it a little bit more. So if you have a really dialed setup, you might be able to do more aggressive overhangs, but in general, people recommend about 45 degrees. So yeah. Overhangs can be found in not only these like sloped surfaces, but you can also find them on holes. So if you think about a hole, the top of the hole is an overhang, right? If you draw like a line tangent to the top of a circle, it's horizontal, right? And it progressively gets more and more vertical as you go down the circle. But at the top, it's quite an aggressive overhang. So let me see if there's a good example. Yeah, here it is. Again, that's why the benchy exists, because it has a bunch of these features. You can see, right now we're like kind of chilling. There's not a ton of, overhang, but near the top, you can see where the stair stepping happens. This perimeter extends a lot farther than the one below it, and it'll do it to the point where it has to bridge across, right? This part has zero support, right? And it's not always desirable because you might have, a little bit of drooping on your hole there. So one way to combat this is by removing that overhang by adding a teardrop. So if you ever download some 3D printed parts that some person like meticulously designed to be 3D printed, you might start to see, or you might notice that they do a lot of these teardrop shaped things on holes. And that's because, a 45-degree overhang is perfectly fine. So if you extend that overhang at the top of the circle and create that teardrop, you create, no significant overhangs, and you're typically fine. In terms of precision, yeah, it's not a perfect circle anymore, but for a lot of use cases, this is fine because you just need the hole to have enough clearance to maybe put a bolt through it, and it's a lot better to have a little bit of extra missing material on top than it not fitting in the hole, right? So that's one technique that I've used and a lot of other people do. There's different variations of this teardrop. Some people will start with a teardrop and then they'll cut it off on the top and have a short bridge. But in general, this is just kind of the basic concept of, how you might mitigate these overhangs. The other thing is bridging. So if you go back to like that H, you can see that, you're printing in midair in between two solid parts that you have already. So depending on how close it is, your printer might have enough cooling that it can manage pretty well. You can see the bottom one looks, pretty much perfect, but as you get farther and farther away from the 2 points, you can see there's more and more drooping, right? Again, the material comes out as a molten material. It's very like liquidy, not hard, not like a solid material. So it'll start to droop if you don't have really good cooling. So I recommend you try to design bridging out of your prints, especially for the final. I stress this a lot, but then some people will make things that require significant bridging. In the past, we were like, don't do bridges. And then someone literally turned in like the San Francisco Golden Gate Bridge, right? And that's a lot of bridges. The part had like very small geometries and it basically like fell apart as we were taking it off the build plate. And we were very sad because we handed it to them and it like crumpled in their hand. So I don't want to do that because, I want your finals to be nice and something that you can, have on your desk or be a functional part for something that you might find useful. So I recommend, you don't do any super long bridges. If it does require bridges, again, if you really need it, I'll add supports if it needs it. But again, it's good practice to design these limitations out of your model. All right, this is a little bit more nitty gritty, but certain parts can be subject to warping and thermal expansion. The process of 3D printing requires a lot of heat, and when you heat up a material, it'll expand, and when it cools down, it'll shrink, right? And in some cases, those shrinking forces can be strong enough that it'll peel the part off of the build plate, right? In some cases, it could be user error if they didn't, clean their build surface very well. But sometimes the geometry of your model can make it more or less prone to warping and stuff like that. One of the big things that like contributes to warping is by having a super long part, right? So if your part is super long and then all, the plastic molecules start shrinking and pulling, the longer the model is, the more force it can generate to kind of curl. So you'll kind of see sometimes on really large models, there might be some slight bowing if their printer wasn't dialed in. The other thing that could contribute to warping is, again, the geometry. So corners, sharp corners specifically, create like higher stress concentrations. So you can see here, this corner of this like cube shape kind of pulled up, right? So those corners have stress concentrations that will curl the parts a little bit more. If you make the part rounded with something like a fillet, that stress concentration is kind of spread out over a larger area, so it's a little bit less prone to warping. So you'll see a lot of people, they'll add a bunch of fillets in kind of that direction, then they'll add a bunch of chamfers in the Z direction. So like in X and Y, you'll see a lot of rounded features, and then in the Z direction, people make fillets. Chamfers instead of fillets. The other thing, this is a little bit more technical when it comes to 3D printing, but some people might experience something called elephant's foot. And it's basically when the printer isn't super dialed in, or some people do it on purpose because they want to squish the first couple layers for better layer adhesion onto the build plate. There will be a little bit of excess material coming out of the nozzle, and because it's kind of squished a little bit, it'll be forced to go out of the model, like the area of the model you had typically or originally designed for, right? So if you see in this like circle image here, there's a little bit of extra material, and then there's a line on where it was supposed to be, right? And if you're making two parts that fit together, sometimes having that elephant's foot will prevent them from sliding into each other. So, one thing to combat that is just having better, print tolerances, having a dialed printer. But the other way to do it is by adding a chamfer into your model. So you can see here that this print was like just, this wall was just straight up and down. But if you added a chamfer on the bottom surface, there's going to be a little bit of free material that's kind of in the model. And if you print it and it elephant's foots a little bit, the extra squished material won't extend past that like vertical wall, if that makes sense. I don't know if I'm wording that super well. Does that make sense? All right. But yeah, so if you look at some of the things that I design, I just add like a buttload of chamfers on the bottom surface, just to prevent that kind of elephant's foot from being a problem if I'm making two parts that interface with each other. Also, it just typically looks a little bit cleaner, just in general, because it looks nice when you add fillets and chamfers everywhere. So that's what I kind of recommend. In terms of tolerances, 3D printers aren't like the most precise machines. They're pretty good, but sometimes you can't really expect perfect tolerances, right? Like a milling machine can get things within like several thousandths of inches, or like fractions of thousands of inches, but a 3D printer typically isn't as precise. So I would typically err on the side of 0.2 to 0.4 millimeters. So, if I make a hole for like a 3 millimeter bolt, like an M3 bolt, I might oversize the hole to be 3.2 millimeters, so there's enough clearance for it to slip through. So keeping that in mind when you design stuff, you might want to add a little bit of tolerance here and there, especially if you have two different 3D printed parts meshing with each other. It's good to add a little bit of tolerance just in case those things don't fit perfectly. But yeah, this is a good example of like kind of the thermal expansion or core tolerancing. This was a past final. This person kind of made this Lego-like model, but then when you tried to assemble it, the pegs on the legs didn't fit inside the body, right? And it's because either the pegs on the legs were a little bit larger than they were expecting, or the inside of the body was a little bit smaller, right? Either of the two could have caused this, but if you added a little bit more tolerance, then it may have made this fit a little bit better, right? Maybe adding that 0.1 or 0.2 millimeters can really do a lot when it comes to assembly. But yeah, that's basically it for today. There is a quiz. I did mention it last week, but don't worry because you have infinite attempts. This quiz is just kind of here to just test if you are listening or not, because I know I spewed a bunch of information. So it's just kind of there to see if you remember stuff. But if you don't remember, it'll kind of correct you because it'll tell you what you got wrong. So yeah, you're welcome to take it as many times as you need. But yeah, that's basically it for today. I think we're a little bit early. Yeah, it's 6:40. So if you want, you're welcome to sit here and do the quiz. If you have any other questions about 3D printing and stuff, feel free to ask. If you have questions about your final, I'm happy to answer them now. But yeah, if not, I'll see you all next week.
Next week is that's
Yes, so next week will be the final class. I'm going to be bringing my 3D printer into class for a live demo. Hopefully it works. Last semester it broke. So let's hope that it works this time. But yeah, also submit your attendance forms because I think we're pretty close from last week, but not fully 90% yet. So yeah. Also, people ask like when the finals due. So the finals not due like next week, but it's due the week after next week. So like after, we have our week 5 class, you'll have another week to get that final finished. And then I typically say it's due at midnight that day instead of, 5:29. So you have till midnight a week after the last class to get that final finished. Again, if you have any questions about your final, please don't hesitate to reach out. People ask me like, hey, is this manufacturable? Like they'll ask for some design feedback. I'm more than happy to give that to you because I want you to have a successful final. I don't want it to fall apart when I give it to you. So, anything, if you have any questions, I'm more than happy to answer them because I want your finals to be as good as you want them to be as well. So, yeah. Any other questions? What's up? Well, so it's the meeting where the CAD files for the final, and we'll have
No, because it is that piece of it. But then it also spend. And also be very detailed. Do these things. We want to do 5 you have to get above a 60 in the lab. Yeah. Think that that's fun. Sad. I got about 60. That's not loud. Yeah. Did you break the rules? Yeah. You did. It should be fun. I didn't miss. Like you're so close to like process the way you're saying. If you do it at the same time, so that's what about it. It's like you want to get over the process part of it. That's not it's like positive stuff. I think there's just a glass of juggling in here and so it just didn't do that. Not to go read the board. Yeah. Don't do that. Do that too. But it's super good. Those are different TA classes. Because they're fucking gone. So don't anticipate to do well in the lab, at least initially. Also, not that just three of them. And he didn't even finish grade two. So class two was basically, I think he gave us an extra day and like a jungle and take like two like 1,000 word emails about like shit we could do. He clearly graded, but he didn't release the grade. I gotta go with just parts of three because my figures definitely did the same shit with my figures. Lab two didn't have figures that much in be too badly. Fuck if I know. What did you do? Oh, that's. Are you in fluids right now?
No.
Oh, okay, no, you have to do fluids first.
Yeah, I
Ah, gotcha. Are you graduating in a semester early then? Because it's so not fall. Yeah. They added it's very much relevant at the like last summer. Senior design, so it's compressed because they're more close. Makes sense. Saves you money, maximum of like $9. It's like, dude, I'll tell you right now, this is, whoa. That is totally great. Wait, it's looking good. Oh, that's good. Right? This is, that's controls two, that's the lot. Is there any way you can? That's not. If through levels, is there any way you can do that? Is controls two, but it always but there's no you rather both slap with it. You're the team who both have arts issue of arts and both have friends blocked the other. And acid two would be first presentation. It's recorded. I was not it's recorded and on the final for but there's both two. Yeah, both of them are absolute two. And we